we start off with some definitions. A multiple, a number that can be divided by another number. 12 is a multiple of 2. If we wanted to list all the multiples of 2, we would start with 2 because it's 2 times 1. Then we go to 4 because it's 2 times 2. Then 6, then 8, then 10. All of those numbers would be multiples of 2 because they can be divided by 2 and have a whole number as an answer. There's an infinite amount of multiples for any given number. They go on forever. Okay? A factor, a number that divides into another number. 2 is a factor of 6. Since 6 is 3 times 2, we will also say that 3 is a factor of 6. So one of the things that we sometimes try to figure out, and what I was talking to you about earlier, is what are all the factors of a number? A prime factor, or a prime number, are things that have no other divisors other than 1 and itself. Prime numbers like 2, 3, 5, 7, 11, 13. Finding prime numbers has long been a hobby of mathematicians. In fact, there's always a competition going on. Can you find the largest prime number? Who's found the largest one? And then mathematicians try to find other large ones. Prime numbers are used a lot in cryptography, in computers, for making sure things are secure, right? When, I don't know if you guys do online banking, okay? I don't know if you do, well, not every day, but can you access your bank account from your computer? Can you see how much money's in there, right? If you wanted to, you could take some of that money and give it to your friend. If you wanted to, you could, oh no, this way I'd probably get in trouble if you took some of your money and gave it to me. But yes, you could. You could decide to transfer money from your bank account to somebody else. And as a result, you have a password to get into your bank account, because Emma doesn't really want me going into her banking account and then sending her teacher money. Then I'd probably get into a lot of trouble, right? So we have passwords to protect it. But how do those passwords work? And what are some of the ideas behind it? Now, to simplify things really easily, we might have something like the code is out there that it is 143. This is for Emma's bank account. And she has to provide one of the factors to check that the code is right. So when she enters her password, she says 143 is 11 times 13. So her password goes in as 11. The computer checks that the other password is 13. The numbers work. They let you go on. Okay? And so if I give you a number like 143, you might say, ooh, that's just outside my times table, but I know that that's 11 times 13. The hard part is if the numbers get really big, it takes a while to find the two things that multiply. And that is how a lot of cryptography works. They have really, really big numbers, and you have to, your password provides one of those numbers that's a factor of it. And if the other one matches up, they let you through. So a company a number of years ago put together a challenge. So I'm going to go here to the internet. Here we go. Wikipedia RSA factoring challenge. So they decided they wanted to find out if people could break these codes. So they gave out numbers and they gave out prize money. So like if I give you 143 and the first person in class to get that that was 11 times 13, I give $5 to. Pretty sweet, right? And you're allowed to use your computer, you're allowed to use your calculator, you're allowed to work together in big as groups as you'd like. You can do whatever you want. So that's what they did. Here is the first one. It had a prize of $1,000. It was 100 digits long. Okay? And the two numbers that multiply to that number, so there's the answer to it, are both very large prime numbers, which makes this extremely hard to find what the answers are going to be. So what they did is they had a computer, in order to make the challenge fair, they had a computer take two prime numbers, multiply them together, get the bigger number, and then they destroyed or got rid of whatever the computer did beforehand, so they just had the answer without any of the work. And so even the team that provided the questions didn't know the answer. The only way you would know the answer is it's very easy to get a computer to multiply two numbers together and say what the answer is. It doesn't take the computer very long. The interesting thing about this, though, to get something to factor does take a long time. Yes?
Why does it matter it's a prime number? Why can't they just use random numbers?
If it's not a prime number, like if I gave you a big number that ended in 8, then you know you could divide it by 2. And so by taking out the 2, your number is now a lot smaller and easier to work with. Right here, let's do one that's not hard. Okay? I say, what times what is 126? Well, you can easily see that that is 2 times something, and you cut it in half, you get 2 times 63. And what times what is 63? 7 times 9. And we just broke this one down into its prime factors quickly, because we could break, taking the 2 out made it easier.
But then why not just end it in an odd number?
Right. So as soon as I end it in an odd number, go. What times what is 221? Hurry. I'm waiting. Right? Do you need your calculator? Right? It doesn't divide by 2. Does it divide by 3? No. It won't divide by 4. Does it divide by 5? No. Does it divide by 6? No, because it doesn't divide by 2, so I don't have to check any even numbers anymore.
Yeah,
So then I have check divide by 7? No. Does it divide by 11? No. Does it divide by 13? Yes. Oh, good. 221 is 13 times 17. Done.
you just know that off the bat.
I do, but that's okay. So these numbers were very, very big. And there's 2 large prime factors. So they gave, as a prize, $1,000. $1,000 prize. And all of these numbers were given out at the same time. Oh, there's the guy that even solved some of these. He made money. Okay? He was the first one to solve it. Okay? They gave him 10 more digits. He probably started these at the same time. This one took him a whole extra year to figure out with 10 more digits. Okay? Another 10 digits took another year. As they went up by 10 digits, look at this one. This one at 150 digits took 13 more years.
When did it start?
Of course, they didn't give out prize money for that one, so maybe people weren't working as hard. Okay?
When did it start?
It should say on here when it started. But look at the prize money later on. $30,000 US. $50,000 US. And so even though this guy started winning at the beginning, this guy here, Jens Frank, who won this one, he probably created a stronger mathematical program to figure this out faster.
Wait, why would they give them money for the number? The number becomes worthless after they solve it.
It becomes worthless after they solve it, true, but what they were looking for is if someone can develop mathematics to figure this out too quickly, then our entire internet might be vulnerable. So we have to figure out how do we keep our internet password strong so it doesn't get hacked. How do we do that? How do we make the mathematics stronger than it was before? Because as we advance in our mathematics and check out the ones at the end that these ones no one has solved. No one has figured them out yet. I don't think they offer the money anymore that the company's timed out. But this one, if we look at this number, wow. Look how many digits that is. It's 617 digits. And there are two numbers that multiply to that. But nobody knows what they are. And it seems like it shouldn't be that hard. But even with computers, and right now there are probably computers that are still working on that, just sitting there calculating millions of calculations per second and still haven't figured that out. And so then we feel that our internet is safe because even if a computer takes 10 years to crack it, by then it's probably going to be too late. Okay, so there is a little history of that. What we are going to look at is prime factorization, which is based on this. If you have a number like 24, could you keep breaking it down until you have it as a multiplication of only prime numbers? So 24 is 2 times 2 times 2 times 3. Remember exponents in grade 9, if you have 2 times 2 times 2, you could write that as 2 cubed.
Wait, so that counts as a factor?
That counts as that 2 happens 3 times. That 24 can be written as 2 times 2 times 2 times 3. If we want to try another one. 54. On your times table, what is 54?
27 times 2.
27 times 2 or 9 times 6. It doesn't matter which one you start with. Okay? After you do 9 times 6, could you break up 9? Yes, it's 3 times 3. Could you break up 6? Yes, it's 3 times 2. Are all of those numbers prime numbers? Yes. And now you can use this, right? Remember before I said, what times what is 54? 9 times 6, 27 times 2. You can use the prime factors to get all of those. Think of all the different groups you could have. If I took this and this, what do I get? 9 times 6. That's 54. But if I decided to take instead this and this, then I'm going to get 27 times 2. That also makes 54. If I decide to take this and this, now I've got 18 times 3. That also makes 54. So if I figure out all the different ways that I can group those numbers together, then I'll figure out all the different ways to make 54. You could also do this one. 54 times 1.